once more here. Great pleasure to talk here. So this will be mostly a talk on two-dimensional conformal field theories with just Virasoro, most of the talk. And as the title suggests, I will only use one part of the modular transformation. So this has been quite successful in bootstrapping the possible allowed data in 2D CFT. So if I look at all possible CFTs in the spectrum in delta and J plane, J is the spin and H is the conformal dimension. Yeah, yes, sorry. So here, of course, by unitarity, this area is disallowed. This is delta equals to J in 2D. Higher D, this is delta J plus D minus 2. So we will always be in 2D. And there are different patches by which we can cover this allowed region. This region, mostly when both H and H bar are kind of small, this is covered mostly by numerical techniques. So here, one actually focuses on quantities near the intermediate temperature, not at high or low temperature. This is intermediate temperature. So I will work with. I'll take the length of the cycles to be beta. Beta is the inverse temperature, and 2 pi will be the size of the spatial circle of the CFT. So this is usually around beta equals to 2 pi, which is 2 pi is also the fixed point of the S modular transformation. The S modular transformation takes tau to minus 1 by tau, which takes beta to 4 pi square over beta. And then people have also some results using light cone. So in here, yeah. So here this region, large spin, this is one of, like kind of a 1 over J expansion. That's how the light cone blocks behave. This is the results from the light cone bootstrap. But today mostly I will focus, in the beginning part of the talk, I will focus on the 1 over delta expansion, which will be this area. So this is usually extreme temperatures.
And very large delta, keeping J fixed.
Keeping J fixed, exactly.
Yeah. How are you going for the light cone in the torus?
No, not on the torus. So this I'm talking about general. Not modular bootstrap here, and also here beta should be viewed as a parameter, because finally I will integrate out beta. Means there won't be any beta, so the first part of my talk will explicitly talk about some results, analytic results in this asymptotic limit. This is also the Cardy regime. This is the Cardy regime. So I will talk about some results from the Cardy regime. Yes. Yeah.
Which is about what would be the extremal limit, which is, when you take J to go, J and delta to both become very large, but it's a little bit like only turning on H and not H bar. Those are the extremal BTZ black holes, and I'm just wondering if there's a interesting kind of bootstrapping one can do there, because those are the things which are dual then to the Schwarzian theory in general.
So so we'll see for some of the analysis, some of these regions overlap.
Okay.
So they will lie in some overlap.
So one quick comment about that is, of course, is that in a theory where you can do it left and right separately, these sort of extremal CFTs, there the torus partition function is actually completely fixed. That's not what you want.
Yeah, and I just want to know when that is the case. When is it that a CFT can be thought of like that? So, like a free theory I know can be thought of, but if I just handed you, I think, I'm sorry, I just have these gaps in my head.
So you could find such states even in CFT without this kind of factorization. When you look at, for example, only the vacuum module on the right, it would multiply only the holomorphic stuff on the left. The the vacuum state.
Mhm.
So in that sense, general CFT, if you look at its vacuum sector, will have just holomorphic operators. So I think this kind of bootstrap would then effectively reduce to a one-dimensional bootstrap question, which people are studying.
And also actually I will also study one-dimensional bootstrap when I will talk about just the blocks, just the holomorphic blocks themselves. They have they satisfy a crossing relation by this Virasoro kernel. So there you can explicitly study H just going to infinite.
Okay, thank you. So you must go on, but just to say,
Yeah.
you know, in the extremal case, it's not the sort of growth of states doesn't seem to be just the Virasoro block. I
No,
mean,
it may not be just Virasoro block because it's a chiral algebra associated with CFT.
yeah.
So it would be a bootstrap of chiral algebras. I mean, I'm not sure if
So
people have
that-
studied this
yeah.
systematically, but a large delta limit
Yeah.
has been studied.
So this is
Yeah.
what I wanted to ask you. There is some chiral algebra. Just
So for example, CFTs with W symmetry, if you look at holomorphic states, would not be Virasoro. There will be spin 3 and so on things also. Right.
exactly. So this is what happens in the D1, D5 analog. In that sort of dumbly speaking, you can do it with free bosons, but you need that extra chiral. In some form. Okay, anyway, I'll come to you. Sorry.
Yeah. So I'll talk in the beginning. I'll talk about some results from the Cardy regime. Then I'll focus on some new aspects in this intermediate regime. So basically, right now the results in the intermediate regime, they all focus just on the partition function, on the torus, and use the modular invariance, and then apply some linear functional at the fixed point, such that it is 0, and that gives you some constants. But one can actually play the same game using torus correlators, because they have some modular covariance property. So one can construct some modular invariant quantity from the torus correlator and play the same game, and we will see that that can also lead to some interesting bounds. So like generalizing this Hellerman Schmidt-Collinet kind of analysis. And then towards the end, I will talk little bit about Tauberian techniques. So this will go back to the Cardy regime. So for so actually we'll see the naive Cardy analysis has a lot of uncontrolled errors. So basically because we are integrating over the imaginary temperature axis when we are doing the inverse Laplace transform. So then only near small real part of the inverse temperature we have a good saddle point approximation. When the temperature is large and complex, then the subleading terms, they oscillate and they are not suppressed. So Tauberian basically cuts off this imaginary axis. So it's instead of considering the entire delta plane, one actually focuses only on a band and does the analysis here.
If I may, where does this adjective come from? Is that the name of a person?
Yeah, it's the name of a person.
What is the name? Tauber?
Tauber, yeah. And this was used, for example, by Hardy and Littlewood to find, basically it gives some constants on averages of coefficients which can, of quantities which has a Q expansion. So I'll very shortly talk about this.
So one is to look at modular covariance of other operators other than identity on the torus, or you can look at higher genus partition function.
Yeah, higher genus is also very, it can lead to also a lot of interesting constants, but I will not talk about it. Actually, there's a paper by Cardy, Maxfield and Maloney where they looked at higher genus quantity, which is the secondary entropy of 3 intervals. So that's a genus 2 partition function. So there you can use modular properties of that quantity to say something about heavy OPE coefficients. Okay, but I will not talk about that. I will just focus on the torus, and because there are still things to do on the torus. Okay, so this is most details you will find here. So I will first briefly sketch some results, some old and some new in the Cardy regime. So the kind of notation that I will use is this. So under T tau going to -1 by tau, if I have any quantity f tau bar with some index alpha, this may be, so say if you have an extra u1, this can be chemical potential. This is related to f gamma -1 by tau bar with some kernel alpha gamma and integrate over gamma. Okay, so for example, for partition function there is no integral, this is trivial, there are no indices, but for say for example if you have vita soro times u1 level k, vita soro bar u1 level k, then for example s alpha gamma is so then alpha are the chemical potentials. So then there are the new chemical potentials and the old chemical potentials, mu bar, mu bar, this is delta mu minus mu by tau delta mu bar minus.
U1 is both holomorphic and homomorphic.
Yeah. Yes, I should have.
Sorry, I
Yeah.
didn't get that. So the second line is the partition function of, sorry, what is f in the second case?
In this case, partition function. Partition function with a u1.
Partition function with a u1.
Yeah.
Oh, why does the partition function just transform more?
There is an anomalous piece to the partition function. So then this is this piece, I pi c k tau bar mu bar square minus tau mu
The
square.
chemical potential was on the time axis and not the space axis. I mean, sorry, why does the partition function not transform more simply?
So this is the partition function y to the power j0, y bar to the power j0 bar, q l0 l0 bar minus c 24, and then I am just changing the modular parameter. Then the partition function is almost invariant except this phase, and the chemical potentials also transform.
Why do you write it as the integral transform?
Oh, because
Delta function in this case.
yeah, here it is delta function. Yeah, so if I look at torus correlators, it will help me, it will be easy to define a modular invariant quantity later when I do this. That's why I'm just introducing. Otherwise, I can just think of just transforming things within this bracket, transforming the y. So this is equal to trace, this is equal to e power I pi c k mu bar square by tau bar.
What this else is doing is to say that the chemical potentials will also transform.
Yeah, chemical potentials will also transform, and also there is this
Modulo that factor.
there is this
just
factor.
transform chemical potentials.
Yeah, so then there are these new y's, y prime j0.
And why is that factor then? Why is that phase?
This phase because this doesn't this one way to see this is just study the free boson. And,
It's because the theory is somehow chiral. This u1 level k is what, please?
u1 level k is so if I look at the jj correlator, then
Sorry, I think Abhijit asked this.
Yeah,
It's only
sorry.
on the left or also on the right?
this
U1
is
level k.
yeah this is so there is a chemical potential also for the right and the left, so for both. So there is a q and q bar. There's a
There are two separate U1s.
there are
both
two
of
separate
level K.
both at level k.
Level K is somehow visible there as an anomaly.
Yeah.
If I
If you want to remember, you want to be large degree module. This is a large degree module.
Well, I mean, it should be a theory that is not well defined then on a torus. The path integral should not be well defined on the torus, right?
Yeah, that's why there is
And
this,
usually that happens when you've got something chiral.
yeah, but also
So your u1 theories cannot be written in some line.
yeah, that's
It is chiral because you're thinking of U1s as separate symmetries.
But there is a
Diagonal, maybe. I don't know how to take the diagonal. But yeah, it is two separate symmetries.
there's a separate U1 for left and a separate U1 for
But I
right.
was just thinking, what about K-free bosons? That would be a theory which has level U1 level K both on the left and right, and that shouldn't have this problem.
Yeah, exactly. I was also thinking, I mean, is this because you're turning on nu and nu bar, right? Somehow nu and nu bar are being turned on. That is
Yeah.
sort of strange,
Yeah,
right?
I see.
Like, what does that mean?
Even that for
It's not just a chemical potential cut out something strange, right? If you just take a U1 theory, you turn on nu and nu bar, which are different.
Yeah. So here they are allowed to be different.
Yeah, but it's not a standard chemical potential I would turn on for a U1 symmetry.
it's for momentum as well as winding.
It's for the
Even if you set the mu bar, it's not going away.
it's not going away.
Even if you said mu bar is mu.
Yeah, it's tau.
Yeah, tau minus it will be proportional to tau bar minus tau. That is right. So that will be
Anyway, go ahead.
yeah. Okay, so this is one example. So this has been used. This property has been used, for example, in papers by Kachru et al. To find to do this intermediate bootstrap to find the gap in the charge also of the lightest charged primary. And of course, one can also write down the torus correlator. Another example will be the torus correlators. Yes.
Getting back to that,
Yes.
as Abhijit was saying, if you turn on a chemical potential for both, it's
Yes.
something odd. But here, even when the two chemical
Yeah,
potentials
it's still not cancelling.
it's still not cancelling. Doesn't that sound funny?
Now, why do you write the partition function not in this integral form? Isn't there is mu minus mu bar squared terms that appears in the exponent? Because that's what I'm not familiar with this integral transform, but if you don't write it in terms of integral transform, you have mu minus mu bar squared.
You're saying the right formula is mu minus mu bar the whole thing squared.
That's what I vaguely recollect from
I see.
That would make more sense.
That would take away these questions, but this is what I remember. So maybe we will check the yellow book. Yeah. Okay, so another example.
So L naught minus L naught bar, I understand that what
Yes.
that means.
Yes.
That's a twist along the torus.
Yes.
So this
J naught.
this of the J minus J bar.
Yeah.
What is that object?
Yeah. So that.
I mean J I know this and with the charge. For example,
Yeah.
in the example that Shiraz was talking about, is the complex boson. So
Yeah.
I know what U1 is. I mean I know what.
Right. That J minus J bar will couple to I think Q plus Q bar.
Yeah, I know, but
yeah.
what's
What,
the charge for that? So
Right.
I mean, what's the
For-
symmetry
Is
for
it
that?
not a winding number? For compact.
Yeah, for compact.
For compact complex boson, it's the
No, complex if you think in terms of radius and this thing.
You're thinking of the phasing of the boson. I think both of us were thinking of just the translations of the boson. L phi is the J.
Oh, yeah. Okay, I see.
Yeah.
This under bosonization will go to phasing of the fermions.
I see.
We can't do bad an anomaly since this fermion
Yeah.
this fermion number is used in string theory as
Yes.
one
Yes.
of the
Yes.
things we gauge the theory by.
Yeah.
But anyway, later.
Okay, another example would be to study a endpoint torus correlator. So that is related. So if I study it on a torus with modular parameter tau, it's related with the corresponding quantity on the S transform torus. But now there are some factors. Is this 1 over tau to the power hi tau bar to the power hi bar product over i's, and also these coordinates, they also transform. I am writing only the holomorphic part. So wl by tau. Okay. So
Sorry,
yes.
just one last. Maybe it is related to the fact that when we try to deal with string theories with left and right
Yes.
separate, it only makes sense in multiples of 8. Maybe that's somehow related. Just please go on. You know,
Multiples
the
of
string, the
8,
GSO
yeah.
projection doesn't
Yeah.
give rise to a consistent modular invariant partition function
Unless,
except in 10, 80.
yeah.
So dimensions. That may be
Yes, it
related
may.
to this, because you've been putting very special value of mu for that.
Yeah, that is true.
It may be the same fact. Sorry.
Okay.
That's always. That's always.
Here, Acha, this is the Cardy. This is how, this is the partition function transform, right?
Yes.
So it's confusing.
I agree. That is mu squared minus, that this form is through I.
Okay, I also actually did not plan to talk about this, just wanted to present it as an example. But most of the talk will be about the torus correlators, just with Virasoro.
Just with Virasoro, meaning no other chemical.
No other chemical potentials, Virasoro and Virasoro bar. Yeah,
And you will have tau bar, so you will have a torus that's not rectangular.
yeah, exactly. So very thin and very long for extreme.
Depending on a chemical potential for both energy and angular.
Yeah.
Therefore making the torus not rectangular.
All right. So, of course, the prime example is the invariance of the partition function, and this the way we do this analysis is we write down a Q expansion for Z. So I will separate out the vacuum part. So this is Z of beta is a 0 e to the power beta c by plus a. And we want some information about these A deltas for large delta.
Sorry, the mass gap to the BTZ, like a black hole in the NS sector, is C by 12?
C by 12.
C by 12.
C by 12.
Thank
C
you.
by 12. So the questions of means if we need a gap to do this separation, that will come here. Okay, and then we expect that only when beta is small, when we are looking at high temperatures, then these guys contribute substantially to the sum. So we expand the partition function here, beta going to 0, and for beta going to 0, we can use the Q tilde expansion, which is a better expansion. I can just retain the vacuum term. So this is approximated by just 4 pi squared by beta c by 2. And later we will see. Okay, and then this integral is written as a Laplace transform. And then to find this rho delta, we just have to do an inverse Laplace of this quantity, and that gives us rho delta, the famous Cardy formula, 2 pi square root c by 3. And later in third part, we will question this.
This is the Cardy regime.
Yeah, this is the Cardy regime. So first part, I'm just focusing on the Cardy regime. Okay, and then one can play the same game also using modular covariance properties of the torus correlators, and this was done, for example, so this Cardy is done by Krauss and Melloni. Where you write down the 1-point function a torus one-point function, you write it down as integral OP coefficients, diagonal OP coefficients, tau delta more correctly to, and here one I should mention that here this naive analysis, this is taking all operators into account, but I can also focus on primary, then I use the character expansion. So here also I should use the torus block expansion. So this is, so we need the beta going to 0 limit of this, so the high temperature leading answer for O for the one-point function, this will be given by, so remember there were some factors of beta, so this is related to this equals to, this was equal to 1 by tau over HO, 1 by tau bar to the power HO bar O 4 pi square by beta.
Large C limit coincide with this. Can you check the answer that you will get from this expansion doing a holographic calculation?
Yes, I'll yeah, there is a.
So is there any particular justification that this Cardy regime and large C regime are sort of like both the limits coincide?
No, they don't coincide, but we'll see that large C helps in justifying this means why the Cardy answer is a correct answer. They don't, this is a separate limit. So for example, if I use the torus blocks, I could have used the large C torus blocks here.
Are you taking large C now?
No, here I am not taking large C.
So the answer you will get here is valid for all C.
It will be valid for all C.
Take large C of that answer.
Yes, but it will not change. It will actually, it's the answer that you will get with this arbitrary C. There will be factors like square root C minus 1 by 24 and so on. So this will not change appreciably. So this is just C greater than 1, so that you have infinite number of primaries.
And here this is not positive definite.
Which one?
C.
This one? No, this is not.
So therefore earlier the quantity that you used is like positive definite quantity. So it makes sense that term by term it should work. Here it might work, but there might be cancellations.
What cancellations?
When you are using modular bootstrap for
Yes.
this quantity,
Yes.
you are comparing two sides. Now, terms in both sides are not, if they are positive,
No,
definitely,
I'm-
the
I'm-
order of magnitude should
So
match.
then maybe you can do what you are trying to do, and then maybe you can raise your objection.
So if you look at the, so I now for in the beta going to 0 limit, I can just use the vacuum result, but the vacuum is 0 for here because vacuum doesn't contribute. The leading contribution comes from the lowest primary, so this gives you 2 pi beta to the power. And if I say assume if I take O to be scalar, this is delta O, and this leading answer is just minus 4 pi square by beta delta chi minus C by 12 times C chi O chi, where chi is the the definition of chi is the lowest primary which has a non-zero OP coefficient with O. So this will be the leading result, and one can take other corrections. So this will always be the leading because delta chi is always positive by unitarity. So that is what you need. Okay. So then one again does an inverse Laplace
Right.
to figure out
Here you
this.
are- Here you are comparing both sides, right? If the left hand side was positive definite,
No, so see, this is the leading answer at beta going to 0 limit of this quantity, which has been written like an integral transform, Laplace transform. Okay, so this is the leading answer of something of some integral transform. So I just want to figure out the kernel. I do the inverse integral transform. Positive definiteness is very important, and that plays a key role in this Hellerman analysis. There we'll see that this the fact that these are not positive always will come back, and we'll need to make some additional assumptions. But here again one can do this inverse transform and one can get an answer for C delta O delta in the limit delta goes to infinity, because that's when the beta going to 0 limit dominates.
Sorry, this is a bit
Yeah.
orthogonal, but if you were to compute 2-point function
Yes, yes.
in this channel,
Yeah,
you would get a square.
you will get a square, yes. So that also we did means people among other people. So we have done means that, and then you can estimate the off diagonal square. You will get an off diagonal square, and you get all these results. So for example, I'll write down this result for C delta O delta. So this is the Cardy answer. I'll keep here.
So
Yes.
you're using the fact that you know rho independently.
Yes, yes. I'm using the Cardy because I'm in the Cardy regime.
So you know rho, now you know this average, and
Yeah.
so you're getting
Some answer for
averaging
of this C.
which, as Indranil says, may differ significantly from the
Actual,
any given.
yeah, any given one.
So, yeah.
And all that,
Averaging over
all
one
that,
doesn't mean
yeah.
but some large delta, I think, or not?
No, so
Large, at large delta,
Yeah.
because you're using the
I'm using the rho delta from the and even if I means one can refine this analysis just for primaries also. Again, one uses the primary density of states and so on, but just the
If you take C large, so you will get some answer from this analysis, which is valid for presumably all C, which is large enough C. Now, if you take C large compared to delta, keep delta fixed and take C large.
yes, yes,
Then you can compare this result with the holographic calculation,
yes,
and that should match.
Yeah.
Does it match?
yes, yes, yes.
Okay.
That matches. So that was also worked out in Krauss and Maloney. So I'll just write down the result. So this result delta O delta. This is proportional to, of course, chi. Chi you divide by this rho delta. And then after dividing and the inverse transform, this is delta minus 1 by C. Pi by C.
So let me just make
Yes.
sure. Left hand side is C delta O delta? Or is
Yeah,
it-
C delta O delta. Yeah. Yeah. So then, and this is reproduced by the following Witten diagram or the following geodesic. So I considered the BTZ geometry, and this is my geodesic corresponding to a scalar dual to O, and this splits up and wraps the horizon. This is the scalar dual to chi. So this diagram reproduces this answer when you identify beta of the BTZ with the ETH temperature, with the temperature of the state delta.
Sorry, this answer is supposed to be correct at delta much larger than
Delta much larger than C.
C.
Yeah.
So the first square root, we can just write the square root delta.
Yeah.
Minus 1 is for
Yeah.
negation. That's in the second square root we
Yeah.
need to keep it.
Yeah, we
Because
need to
that's
keep.
delta of
Yeah,
chi.
yeah, that is delta of chi.
And I see, and delta of chi has to be smaller than
Yeah.
C by 12.
Yeah, yeah, yeah. That also.
So this is a proof that delta of chi has to be smaller than C by 12?
No, because there are also some imaginary phases here.
Oh, so it could be larger.
It could be larger, yeah.
Okay,
Yeah.
fine.
And these imaginary phases actually depend on the spin of O.
Okay, so the end result is that the thing decays like 1 over square root lambda,
Yeah.
like e to the power minus
Yeah.
square root lambda.
And this is important for thermalization of heavy states, because this is what appears in, if you calculate quantities that you want to approximate by thermal quantities. This OP coefficient appears.
And then the actual coefficient of that decay depends on the lightest state it couples to.
Yes,
But otherwise the square root lambda
Yeah.
delta is square root.
yes, yes, yes.
No, I meant coefficient
Ah.
of that.
Yeah, yeah,
Yeah.
that.
That's very interesting.
Sorry, could you relate once again with the BTZ black hole?
BTC black hole. So this geodesic diagram reproduces this answer, where
But that's what we expect because from this Schrodinger analysis, that's we know from that's the correct density of states now.
yeah, but how will you draw the geodesics?
Okay.
So this This factor is basically coming from this wrapping, this guy wrapping the
This is
horizon.
black hole's temperature is set by saying that the corresponding energy density
Yeah.
is equal to delta.
Yeah.
Roughly, that's the
Yeah.
relation.
Yeah.
Interesting. So, I didn't understand your comment about the exponential fall-off being robustly 12 delta over C, or were you talking about?
No, that is e to the power minus square root delta times some number. That
Yeah.
seems robust. Right?
This number.
So that the average coupling of any operator to other operators of dimension delta
Hmm.
always scales like e to the power
Minus square root delta.
That's what he's saying.
For heavy operator, for
For
very,
very high.
very, very high.
O is taken to be heavy.
No, O is
the base, right?
O is some fixed. O is fixed. O
Chi becomes heavy.
O appears basically there is some polynomial
Then
dependence.
this is valid. Oh, sorry, not carry, well, delta.
Yeah, delta is fixed. But delta is heavy, but there is some polynomial dependence on O. So there is some delta to the power, delta O to the power minus delta, some function of delta here.
So there is an exponent in delta also then?
Yeah, there is a log delta O.
No, delta appears in the exponent of the thing that you are.
Yeah, delta appears in the exponent here. So there is actually. So I'm not sure about this factor right now. 1 second, I will look it up once.
Deltas are very important.
Yeah, I'll just tell you what this factor is. Yeah.
Like something that you can control for large.
Yeah. So this is okay. Sorry. This is delta minus c by 12 to the power delta O.
Oh, so that is more important than the e to the power minus square root delta.
What is delta?
Delta naught is delta. What is it? Yeah. Sorry, delta O. Then
Delta O. That's why. Yeah.
What is delta?
Delta O is fixed.
The dimension
Number.
of O.
Dimension of O, which is fixed.
Okay.
In the
Right,
size.
right. So it's not a very important.
Yeah, not a very important factor. It's a log. It's a log.
Just
Yes.
didn't fully understand. So, I mean, O in general will couple to, on the torus to
To-
light operators
and also heavy
and
operators.
so on.
Yes.
And what regime are we in?
We are in the regime that delta is much larger than all possible scales. C, delta O, delta chi, and so on. Yeah.
Where is this used, this approximation?
This approximation is used. I am using Cardy formula, and I am using this dominance. I am just using the leading order result.
So then that the
Lightest
state dominates.
gives you the high.
You don't just need the large temperature for that?
No, temperature is large, but also delta needs to be large, right? Because beta is small, so that's why I can get information about large delta.
Yeah. So just 2 seconds.
Yes.
So You used the modular transform and you went there for, so beta was small clearly,
Yes.
and what you're assuming about delta chi, chi is the guy, I'm a little confused. Chi is the dominant guy after doing the modular transform which contributes.
The
Exactly.
lightest operator.
Yeah.
The lightest
Yeah.
operator.
Yeah.
Apart from it.
Yeah, because identity is not contributing.
Thank
Yeah. For 2-point function, the contribution will be universal because there the vacuum contributes. So for 2-point function, the answer will be, I will just write down.
Sorry, just 1 second.
Yes.
This delta O delta being equal to something,
Yes.
that delta O delta was supposed to be within an integral. What happened? to
No,
that?
so I have been inverse. I have done the inverse Laplace transform.
Oh, you did the
I did the inverse Laplace and divided by rho.
At this level, we're just doing thermodynamics.
Yeah.
We're trading temperature for anything.
For delta.
It's very nice. Very nice. I wonder, is something like this known in higher dimensions? That there's an universal e to the power minus delta
No, actually.
coupling.
One can think of doing this in higher dimensions.
There's a natural conjecture, right? Because it's square root is d minus 1 by d.
That is right.
It's the density of states.
Yeah.
So it's in the natural conjectures that's always
It couples like that.
Natural conjecture exists.
ETH is such a good.
And it's d minus 1 by p.
Of the order of entropy of those states.
ETH says that if delta is high enough, then you replace it by some thermal state, and then W over that. Roughly.
The corrections are e to the power minus.
Minus entropically suppressed. So that becomes clearer. ETH, the statements of ETH becomes clearer if you look at the 2-point function. So because then you can probe off diagonal elements. So then you start with 2-point function separated in time, and this has the spectral decomposition into energy and delta prime, delta O delta prime square e power t. So then this is like a Fourier transform and a Laplace transform. And then again one can look at the beta going to 0 limit of this, which is universal, which is given by some power of this given by sinh 2 delta O pi t by beta times some power of beta. And then basically to extract this guy out, one needs to do an inverse Fourier and an inverse Laplace, and and now divide by 2 density of states factor. So that gives you, just write down the answer. Delta O delta plus say omega mod square. This is rho delta plus omega by 2. This gives the entropic suppression. This gives the entropic suppression. This naive density of states factors times mod gamma delta O plus I omega by 2 plus omega by 2 C minus 1 mod square. And this gives the gray body factor. This is the of a black hole at temperature which is the average of these 2 states.
So I'm thinking of it this way, and you tell me it's okay. I'm sorry to delay.
Yeah.
I've got a very heavy state, then I act on it with a very light state.
Yeah.
Now that
Changes
it in some roughly random way.
Yeah.
So the total number of states was e to the power entropy.
Yeah.
So the amplitude that will go to any one particular state,
Yeah.
maybe the state itself,
Yeah.
is e minus
Yes.
e to the 1
Yeah.
over e to the power entropy.
Yeah.
But then what puzzles me is that additional factor. It's not quite entropy. It's this light state dependent.
This one,
Yeah.
but here it is going to the same state. Here it is clearer.
There it is clear.
Here it
But
is
let's
clear.
look there.
Yeah, there. Okay.
Then there is
Yes.
some structural dependence on the light.
On the light, yeah. That phase space.
It's not just purely random.
No, not just the phase space.
Yeah, it's
Yeah.
very interesting.
Yeah. Yeah.
I was thinking that you take some very complicated state, you hit it, you add a little bit of energy. If you don't know anything, you'd say it's just evenly distributed among all states of the same energy.
Yeah,
So
1
you
over
get 1 over entropy.
rho delta. Yeah.
But you're not getting quite 1 over entropy.
So that first E is 1 over entropy.
Well, yeah, exactly.
Yeah, this-
exactly. That's sort of, I don't know the coefficient, but sort of, it looks like 1 over entropy, and then the coefficient of that is modified in the exponential, in some detailed
No, this is exactly the 1 over entropy.
and it's the power 1 over.
Yeah.
Excellent.
Yeah.
Then it's multiplied by that
Yeah,
bracket.
yeah, multiplied by that.
Which changes it significantly.
Yeah.
Ah. So that's
Here, these factors are clearer.
yeah. So
You
because
you
it's
pick a
universal-
state and you go to a state, and these are the number of ways you can go to.
Yeah.
I mean, is it related, is it a more refined version that, delta, if it's delta plus, but then this chi is new?
Yeah,
Yeah.
it's some low energy thing, right?
Yeah. That's why it's kind of non-universal. Here, for the universal part, these phase space arguments work out fine.
What's interesting about that, it tells you that these arguments about randomness are not always correct. Right?
Not always, yeah.
I mean,
It depends very sensitively
there's
on
some
the
detail.
detail. Yeah.
Yeah.
That's right.
Also, it's non-universal. Yeah, I mean,
Yeah.
it depends on some other stuff called chi.
Yeah.
Depends on
Right.
the safety.
Actually, also one can find a bound on this guy by using this result. By just using the variance is positive. That gives a bound on the light. How strongly this light couples. That depends on delta chi.
And that rho factor is like the entropic factor?
This factor is like the entropic factor. Here you start with a state, hit it with something, go to another state. And this is basically pick a state with probability 1 over rho delta, pick another state with probability this, and this is the number of ways you can do it. Okay, and you also get this factor, which is this black hole absorption factor. Okay, the quasi-normal mode.
So there is no ETH interpretation of this
Of-
one-point function.
Of the 1 point function, no.
Yeah.
No. For this, there is, of course. Yes.
Say again, what is this? This is the quasi-normal mode, whatever absorption or something.
Yeah.
For a black hole of the corresponding.
Of that temperature.
Even with the omega change.
Why would you say there's no ETH interpretation of the 1 point function?
Because
Because of that strange
dependence on chi.
But in ETH off-diagonal function, there's like entropic suppression, but there's a function multiplied, right?
No, but that function is all in the neighborhood in the energy. The
Yeah.
sky is
Very far away
it's a
from
very
delta.
light, it's a very light state, very far away from the.
All right. Okay, so then there's more of these kind of results.
In the Laplace transform, the integral that
Yeah.
appeared was integral rho delta C O delta delta, right?
Yes. Yes.
So if there was just entropic suppression, then this would be cancelling that, right? But there could be some, I mean, I don't understand a priori why this kind of thing to expect, that it's always
Entropic.
suppressed and so on. These are different variables, so why should I expect this?
You mean? Yeah. So
You
this-
have this E delta, rho delta, and C. Now you are saying somehow this cancellation of rho delta, C delta is somehow natural or something.
Just look at C delta delta. If you think of it as the
Amplitude.
that you take a delta, hit it with an O, and you go back to a delta.
Yeah.
So you've taken something of energy E, you hit it with something of energy E prime, you're going to something. And then you've got some space that you work.
Yeah.
If you were random, you would divide by the total number of states you would go to.
But there is a whole lot of couplings involved, right? How things couple. That is what is carried by C.
C.
Exactly. So it's saying that the couplings are not essentially just
Random.
random.
Okay.
That is importantly enough
Right.
to overwhelm the phase.
So far everything is on the torus, and the theory is that if everything is consistent on the torus, every higher evidence is consistent.
Hmm.
Separately here you can get this kind of data from Eigenstate Bootstrap and try to
Eigenes will give you
check that if they are matching with the things in the torus.
Eigenes, for example. Yeah, you're right.
The kind of C
Yeah, say. So this is Cardy-Maloney Max field. So here. 203. So this partition function, for example, will have factor C123 square. C123. This which there are 3 betas. This will be C123 squared rho for each of them, and there will be e power minus beta 1 for each of them, delta 1 beta I delta I sum over I, and there are modular properties of this guy. From there you can extract this thing again. Then but this turns out means the modular properties which are, so here it's a matrix, the modular transformation with a higher genus. So there modular properties well only at boundary of the moduli. So that actually gives you when these are all heavy. All 1, 2, 3 are all of them are very heavy. So here you see it was 2 heavy and 1 is kind of fixed.
But what about, don't look at partition function, look at one part function.
1 point function.
And don't go to
Yeah. But
maybe
that
minus 2.
that will give you some higher moments of OP coefficients. Okay, very good. So then another thing that you can do in 2D especially is use the crossing. You can write the crossing as a modular property, as a S transformation. So in this Zamologic of this pillow geometry, where
Crossing of what point function?
4-point function on the sphere. So yeah, so O1 infinity, O2 1, O2 Z, O1 0 is equal to, so 1 and 3 are exchanged. This is the crossing equation, and now one can go to this pillow frame, which is related to the cross ratio using these elliptic k functions, and one can again define a norm for I pi tau, and then one can actually write down a Q expansion for the conformal blocks. So this was done by Zamologic of 2 because there are no closed expressions for the Virasoro blocks. So there is a way to find, so basically this is given by I, so this is in this channel.
This mapping introduces some angular deficit.
This mapping, you mean this mapping in, sorry.
At every point of the insertion.
Yeah, so those are those points are fixed points. The insertion points are fixed points of this mapping. So there are deficits at those points. That is true. So this S channel decomposition is 1 to I squared. So then there are some functions 2, 1 HI.
These are twist operators or not?
No, these are arbitrary primary operators. Twist operator, then it is naturally related to the higher genus partition function. Yeah.
This is now on the sphere.
On the sphere, but there is this special conformal frame where you can you can write down a Q expansion for the conformal blocks.
And basically you take infinity 1 minus z and 0.
Yeah. So you see, if I change z to 1 minus z, tau goes to minus 1 by tau. So that's why this z to 1 minus z is like a S transformation. And this is lambda bar 2, 1, 1, 2, hi bar, q bar times this times these h, which are called the Zamologic of recursion blocks. Hi, that depends on all the h's, q, h also for the anti-holomorphic q bar, and there are there's a Q expansion for these guys, and Zamologic of gives a prescription to find recursion relations of these C's. But these are complicated recursion relations, and the computing time to determine these grow as order n cube log n square. So we don't need the details of the recursion, but I just want to say that for large n, these are very difficult to compute. But one can get the large n information very easily using the S.
And physically, the limit you're going to this Q expansion is the
Yeah, so basically q going to small is also z going to small. If I plot the cross ratio small is also q going to small.
Which is the same as well.
Yeah,
right?
which is the same as that. And this z going to 1 is basically beta going to 0 here.
Lambda, what are lambdas?
Lambdas are complicated functions. Yeah, they are kinematic. They are, but they depend on all the external. They also depend on all the external operators and the internal operator. But they are known functions. These the lambda functions come from this conformal change. This is the Liouville factor from the Liouville factor.
Should I think of some torus picture at all, or should I just think of this as a formal Higgs much? If I think of it as a torus picture, where is the data of all these operators?
This is more like a pillow picture. So this is basically torus mod Z2. Z2. So this gives you actually a pillow. So this is 0 to 1 again. Sorry, 0 to 2 pi. This is 0 to beta by 2.
So these operators.
So operators are here at the fixed points of this, at the corners of this pillow. So this is still topological sphere.
But just again, physically, I mean, you work in one channel where you've separated the two guys and only light guys run.
Yeah.
You work in another channel where you guide this guy and that guy, this guy, that
Yeah,
guy.
yeah.
And that's sort of everything.
Yes, yes.
So just to ask, this is elementary. I mean, in one case, the middle O2 is close to the one at 0,
Yeah.
and in the other case, it's close to the point, the one operator at 1.
What one? Yeah.
So you sort of have it either very close to one or the other,
Yes.
and then you do the OP
Yeah.
in that way, I presume.
Yes, yes.
Right. But of course, you're looking at a place, the operator has some fixed position.
Yeah.
And you're looking where it's close to one of them.
Yeah, exactly. Yeah.
But then you do the expansion in the other channel.
But if you replace now
Hmm.
all these O operators by identity operators,
Hmm.
does this manifestly go to partition function?
It should go to partition function.
That's some triviality.
No, but it's becoming a
So-
torus partition function, right?
No, it is not.
Yeah, I agree. So that's what
It will. I think it should go to 1, just 1, because I think these CNs will all collapse to 1 because these CNs depend very sensitively on the external
But if I
dimension.
think of this as a T2 mod Z2,
Yeah.
partition is not T2 would be something, right?
Yeah. So right. One should keep in mind there are these. You're right. So.
I'm saying because of this
Mhm.
funniness of the map,
Yes. Yes.
it may give you some non-zero answer.
But. But if all the h's are set to
It's
0,
a Liouville factor.
Liu, yeah.
Universal. Universal and non-zero. Maybe. Yeah.
The Liouville factors are these factors over here, which are means they don't depend on this, whatever the recursion is running here. So
Right.
these,
But I think Abhijit's asking, in the end you've got a geometrical picture, it looks like
Yeah.
you get something non-trivial.
Yeah, yeah.
Even when you should get the original thing was trivial.
right,
He's
right.
asking how is that consistent? And I think
Yeah.
his proposal is that maybe everything non-trivial is just a Liouville factor away from one plane to the other.
Yeah, that
Makes sense.
can happen.
Can we do Lorentzian bootstrap? Because, for example, we know something about right cone bootstrap from other means. Now that should transform to some sort of a bootstrap in this new tau coordinate.
Yeah, but that means you want to analytically continue this Z.
Okay, so far it's Euclidean.
Yeah, that is
So
right.
you can go to Lorentzian with analytical.
Yeah,
I think
but-
that will do something here.
Yeah, I have not looked at that, but maybe one can.
You have to think of tau and tau.
Yeah.
Right. And because there are some results available in light cone bootstrap, so probably we also
So actually, you're no. This is a good point to raise, because actually I think I take it back. Kusuki I think has looked at this regime, this analytic continuation of Z. So Kusuki, Kusuki. this year itself. And so he has some results about the Zamanovich coefficients, means using the light cone blocks, and actually what we will do matches with his results.
But you can't extract something more from this application. All I'm saying that asymmetric bootstrap is
Yeah.
for partition. Asymmetric bootstrap for partition function is like very much known, which is the one that is mapping to this OP limit. What does this Lorentzian one at least map to in bootstrap language?
Hmm.
It is new kind of bootstrap.
No, no, it's not new. It's, okay, so yeah.
So this, the fact that the elliptic norm here is the square root of the usual one.
Yes,
So
yes,
this
yes.
is the coefficient.
Yeah.
The Z2 coefficient.
Yeah, yeah, yeah.
that is right.
Beta gets halved. So here actually again once again if I study the beta going to 0 limit, that will give me asymptotic results for C12 heavy squared. So that is 1 and 2 fixed, and the intermediate channel is going heavy. So I'll just write down that result.
This below map thing,
Yes.
I mean, I know of, so if in the points were at infinity 1x and 0,
Yes.
then I know that there is a map called Christoffel-Schwarz transformation,
Yes.
which makes
Finite.
those
Into a
rectangle.
rectangle. Yeah.
This
that
is like 1/4 of a torus.
Yeah, but
Is-
that still won't give you a Q expansion.
it won't give me a.
Means basically that
it's
the
the functions that come there, the
Fun-
elliptic functions.
will it still be will the crossing still be like a S transformation?
I don't know. I mean,
Okay, that is the main thing which is used. Yeah.
Probably it's that once you map the complex term to the torus. So this is a unique holomorphic mapping probably. This is the one that
Yeah.
is.
There the periodicity is like that rectangle is like 1/4 of torus.
Even if it is not rectangle, you can have this map. Maybe it will map maximally.
Probably. Yeah.
This K,
Okay.
what function?
This is the elliptic K function. It's this integral of 1 over square root of some quadratic. You can write down in terms of the inverse. You can write down in terms of hypergeometric function. I think Z is some hypergeometric function of Q. Yeah. Okay, so the answer again here is yeah.
Random question,
Yes.
because I came with something, but like, it probably wouldn't buy you anything if you did this for like other quotients, right?
Other
Like if I use the same map,
yeah for
but then if I was considering different,
correlators.
different quotients of the torus, would that probably wouldn't buy you anything new, right? Just that those functions would change. It's generally curious because like I think I know how to do that for different quotients.
For different quotients.
Yeah, but I don't know if that would give you anything.
These functions will definitely change.
Right.
These are the Liouville factors. But
Yeah, maybe we can.
because but these are important because this is what you inverse Laplace transform, these functions. So but then that will be a different kind of Q expansion, right? Because that will be beta divided by some other number.
Right, exactly.
So that should be somehow consistent with this result. So maybe one can check.
Maybe we can talk.
Yeah. So the thing that you get from here 1 to delta square delta going to infinity is 2 pi c minus 1 by 12. This kind of again entropic suppression. And here one has also used the fact that in the beta going to 0 limit, one can of course use the Q tilde expansion of this guy, which is just contribution from the identity. So this is 1, and this is just 2, 1, 1, 2, 0 e power minus 2 pi by beta square, 2 pi square by beta, 2, 1, 2, 0 minus 2 pi square by beta. And one knows, and then one writes this as an integral that one needs to invert. on the string, but this one. And this integral will be dominated again by large I, because one is looking at beta going to 0. And we are using the fact that these have a 1 over h expansion. This is also goes like 1 over h expansion. So these are also not there anymore, so that's why one can extract this quantity. And this is what one gets.
The Q expansions of the H's, are they like nice, well-known Q expansions?
No, these are very difficult to find, the Q expansion of the H. So there is a recursion relation for this.
So you can determine that.
You can determine in principle, but they,
So it's not known whether they complete with some nice object, some
No.
nice modular object.
that is not known. But I'll tell you more about these coefficients now, because there is a more powerful crossing relation, which is the crossing relation of the blocks themselves.
Sorry, this part can be given high dimension. This is just
But-
crossing of some 4-point function.
Yeah, but I am using this conformal mapping.
Details you're using.
Yeah, detail I am using.
But the physics seems the same in a higher dimension.
Physics.
Unless you're using the fact, unless it's very important that you're using the Virasoro block rather than the SN2R.
These H's finally give you the Virasoro.
I
Block,
understand.
yeah,
You're
yeah.
using the Virasoro block, but the basic
Yeah.
physics seems the same, right? You're just doing crossing and trying to estimate how many.
Things are exchanged. Yeah.
But-
The-
Feels like it should have an extension to higher dimension. Is that wrong?
Well, yeah, why can't you do this directly on sphere? Why do you need this map?
because I wanted to focus on, I wanted to pick up the vacuum contribution. So I needed a,
If you do S-channel, D-channel business, can you not go to a regime where only
you can.
And is that regime the same as this regime, which is good high temperature regime? It doesn't look so, right? Because,
no, that is not.
That regime would be light cone regime, as
Yeah,
you
that is
saying,
not,
but
I think,
it's
because,
going to be an OP image.
yeah, because if you
So why is
plot,
that?
if you plot Q as a function of Z,
If it can be done in position space, you might as well do this in the hybrid image. Any
no, but I think,
I'm asking why is it that
Yeah,
after doing
yeah.
this map you are
because of the exponential suppression. There you get a polynomial. So the blocks are polynomial in Z's.
yes.
But here this is exponential in beta.
Okay.
So that's why you can cut off the non-vacuum contributions. Your
How did this happen? It's magic of this map.
Yeah, so it's because of this map. That's why these have a all these functions, they have a Q expansion. Yes. No.
What is beta in terms of Q, etc.?
Yeah, sorry. This is e power minus beta over 2.
So you take the limit of
Beta going to 0.
beta.
And Q was what?
Q was e power I pi tau. Tau is related to Z.
Right. And Q in terms of Z was Q polynomial in Z.
Q is like it's a very it's
Q is a Z expansion.
Q.
So basically, in limits it would be.
It will be
polynomial in
some
Z.
polynomial.
So then the fact that you get an exponential suppression is just that you're writing it in different variables. Exponential
Yeah.
related variables.
Yeah.
So doesn't sound like there's physics in that.
Yeah. And because in any dimension your correlators would be functions of Z and Z bar.
Yeah.
Formally you can do this map separately for Z and separately for Z bar.
Yeah.
So one I don't quite see
Why this
how
is
this particular limit gave you something while it's analog in the Z variable will, even if you use the appropriate variables, the exponential variables didn't. And then secondly, why can't this
in higher dimension. But in higher dimensions, yeah, we can do this mapping here.
Just to say, everything previously you did really used two
Really, we
dimensions.
use
The
two
torus is the
dimensions.
torus,
Yeah,
right?
that is
It's
true.
not S3
Yeah,
minus
yeah.
S1.
Here, yeah,
But here,
yeah,
this was just a trick. something
yeah,
like that.
yeah. It's a trick. That is true.
Okay.
Yeah, I mean at least for bootstrapping these guys. But now I'll use this trick but still, but now what I will say is very specific to 2 dimensions, because that is a crossing relation between the Virasoro blocks using the Virasoro kernel.
Sorry, maybe lost, you should go on, but
Hmm.
Q, beta going to 0 is therefore Q going to 1,
Yes.
and that means tau going to 0. And what does that mean in Z?
So Q going to 1 is also Z going to 1.
Is also Z going to 1. And you were using it to obtain C12 delta square, where delta is presumably
Heavy.
an operator of big temperature.
Yes. So this is the full crossing of the correlator, and that bootstraps the C12 delta square. But say I am interested in knowing about these Zamoda-Chekhov coefficients. So these 1 plus Cn q power and these Cns, which are difficult to compute numerically. So then what is useful to use is the crossing of the blocks themselves. So
Sorry, but H was a was what? Was a block.
H was part of the block. So I'll write down what
I didn't understand what you said. What,
yeah.
what are you
Oh, sorry. So H. So this is this equals to this equals to I C1 to I squared F 1 2 sorry 1 2 3 4. This is the block H in the S channel HI, and depends on the cross ratio. These are the blocks. So this block equals to this lambda times the H. And lambda has a known Q expansion, is analytic, and this has a Q expansion whose coefficients are determined recursively, and we want a formula for these guys when n goes to n is large. So then it's useful to use the relation between the crossing between the blocks themselves, which is given by integral d alpha s by 2i. I'll tell you what alpha s is. Q by 2 plus I. Hmm?
6G square.
Yeah, 6 decimal. SZ plus there is also a discrete contribution. No, this is known from 1998, but used recently for in Bootstrap. This is Teschner and Ponsert and other. So these are some discrete. So this alpha is a parameterization, Liouville parameterization for H. So this is like the momentum. So this H is alpha, Q minus alpha. Q is related to the central charge, and Q is also written as B plus 1 by B parameterization. So here there is a, so this is for individual blocks. And again in this frame, if I go to this frame, I can use this relation to write a.
What is that summation?
This is a summation over. So this is the integral over when alpha s goes over q plus 2 plus the imaginary axis. This is the contour along the imaginary axis, and this is a summation over. So this kernel also has some poles. So this is a summation over those poles. Because to go to this contour, one has to deform the contour, and then one picks up these discrete contributions.
And the original block was for the exchange of some real.
Yeah, there is some real.
Not some Q by 2 by.
Yeah, no.
Okay, some real.
So actually, these are the physical ones. These are the physical ones. These are because this is in the alpha variable.
Physical in the sense of Liouville theory.
Physical in sense of Liouville theory, yes. So then one can actually again write down, really write down a formula for these CNs. So Cn in the T channel, this is the inverse Laplace transform of beta n by 2 lambda 3 2 1 4 ht minus beta by 2 times this right hand side. This right hand side, and so one actually can also compute these integrals. It's a little takes time a little bit to do these integrals because these are very complicated functions. They have poles, double poles, branch cuts. So, but then one can find some form for these CNs. So it turns out that these CNs, so these CNs one can think of as the density of states exchanged in the channel. So these CNs are the CN in the T channel which we find. So these are like the density of states exchanged in the channel, and that has two contributions, one coming from this continuum piece and one from this discrete piece. The contribution from the discrete piece gives the exponential growth of Cn, and this only and the continuum piece gives only a polynomial growth of Cn. So so I'll just, for completeness, I'll just write them down. So Cnt, then there is e power 2 pi c minus 1 by 24, and this is only done for just the holomorphic part, because this is a relation just for H with just the holomorphic part. So here this is Hj minimum. I'll tell what Hj minimum is, times this is exponential in n, Ht plus n minus c minus 1 by 24. Hj minimum is the minimum of H1 plus H2 or H3 plus H4 in this channel, and this comes from the discrete contributions, and from the polynomial from the continuum contribution you get Ht plus n minus c minus 1 by 24 to the power 2 sum over all external operators minus c plus 9 by 4. And if all the external operators are in the continuum regime, then you don't have this piece, you just have this piece. So the behavior of the block, behavior of the things exchanged changes a lot depending on the external dimensions. And if you take all of them to be same, all the operators to be same, this happens precisely at h equals to c minus 1 over 32. And this was noted earlier analytically, numerically. So here we can see this, that the behavior of the block really changes. So this, I don't think there is any explanation for.
So it changes when you move from this imaginary axis.
Imaginary axis. So and basically this starts, this exponential behavior starts to become more important as soon as the external h exceeds c over 32. This is what happens. Okay, so this is all I wanted to say about this Cardy regime.
Yes, sorry. And now you're talking about the large C expansion of the Virasoro block.
No, I'm not.
No
No large C.
Okay.
No, I'm just using this parameterization, but no large C.
So these are exact answers.
These are exact answers. C greater than 1. Okay, but now I want to briefly talk about this intermediate regime, because here I think there are some quite interesting bounds to be found. Okay, so this is, I think, so most of what I said is slightly old work. and or it uses also older work. Okay, so for the intermediate regime, one actually looks at a modular invariant function and applies a linear function of a specific kind to the power p, where p is odd, and evaluates it at the fixed point 2 pi. So this is 0 because basically beta del beta is minus beta prime del beta prime, where beta prime is 4 pi square by beta. So this operator with p odd acting on a modular invariant function is 0, and this is used heavily. This was used by Hellerman and Schmidt-Collinet. So when G was the partition function, that is the first thing to try.
That's not the constraint, that's just the evenness of the symmetry of the partition.
Yeah, but this will give you constants, because this acting on the beta expansion will give you polynomials. So polynomials, so basically this Z, if I do for all operators, then
So I mean the functional that you would use is for even p, right?
no, odd p, odd, because I want the minus sign. I want this thing to become minus of itself. Okay, so then the polynomials that you get for the partition function are of this kind, BP. These are the Bell polynomials. This is 0. With this Bell polynomial,
Polynomial cares about the operator.
yeah, delta is the argument of the.
No. So you applied some very special operator which was odd,
Yeah, P.
but it depends on the operator. Which operator you are acting on the function, that pulls down those factors.
Exactly. Yes. So this Bell polynomial, this is a generating functional for something called these have some name, Stirling number. These denote the number of non-zero partitions of counts the number of non-zero partitions of P. So for example, B say B3, B1 of x is just x. B
Different, every time you hit a partition function with a del by del beta, it pulls down.
it will pull down these.
And then because there's e's and del by del, you
Yeah,
get all.
exactly. And you have to evaluate it at this self-dual point. So this is of course three objects you can put it in non-vanishing partitions.
Didn't get this function. So
Yeah.
This is a polynomial that you obtain
Yeah.
is highly dependent on the operator that you have acted on.
Yes,
If
exactly.
all operator
Yes.
will give you this equation.
Yes.
But the fact that you obtained such a beautiful polynomial
Yes.
depends on the beautiful.
Of course, yes. So this is so the entire numerics is to come up with this linear functional analysis is to come up with good functionals to act on, linear functionals to act on the modular invariant quantity.
What about extremal functionals in this context? This Mazak and company's extremal.
Yeah, so this I have not followed actually, but then they are also using this fact that 2 pi is a self-dual point. This is x cube plus 3x square plus x, because these are the number of ways you can partition 3 objects into non-vanishing sets. So then you consider say then say this I call FP acting on Z of beta is this.
Why did you care about linear?
Oh, because I want this same exponential factor, because I want to look at just the sign of this guy, because this is always positive.
This is always positive now. If you had instead of beta del beta, if you had let's say beta cube del beta,
Yeah.
that will be like.
But that is beta. So I use this guy, right? Beta del beta is minus beta prime del beta prime. But beta cube del beta is not minus beta prime cube del beta prime. It is linear, but it doesn't have that property.
So you use one thing is that it is odd,
Yeah.
which is this line that
Yeah.
that you have written, and the other thing is that do you want it to be linear in beta or not? Maybe you don't know.
No, not linear in beta.
Any operator which is odd, you can use it.
Linear operator.
The physics is simply that the expansion around of G around the beta equals 2 pi
Is-
simply an even modulus, right?
Yeah.
So that once you go up,
Yeah.
in this order there are m equations.
Yeah.
You can express them how you want. But there won't be more than m equations.
Yeah.
You can't-
There you can translate between those
then you can
equations.
move to
Yeah.
different basics.
Right, I was trying to understand if there is any worries about this is
That
the point, right?
optimization problem.
Organizing the mere
Yeah.
conformal.
Right. But if you take m derivatives, taking no more than m derivatives, you can't get more than m
Yeah.
equations.
So then one can consider also different combinations of different p's. Right. So if you consider f3 of z plus a f1 of z is 0. So basically this this gives you, so within the summation this gives you this b3 of minus 2 pi delta plus pi c by 6 plus a b1 minus 2 pi delta plus pi c by 6 times this 0. Now this object actually has 3 roots. This is a cube in delta, so it has 3 roots. So the roots are at delta 0 equals to c by 12 and delta plus minus equals to c by 12 plus 9 plus minus 12 pi. So basically what this is telling you is that now say I want to turn off the vacuum contribution because that is always there. So that I can do by choosing some value of a. So it turns out that if you choose a to be less than minus b3, basically with delta equal to 0, I want to turn off delta equal to 0. So pi c by 6 over b1 pi c by 6. Then of course only delta between these ranges will give you positive contribution. So there must be a delta between these ranges. And this delta plus, so this gives you a kind of upper bound.
When you say less than equal to, you are
Yeah.
not turning it up, but rather making it negative. I mean, either non-positive, right?
Non-positive.
Making it non-positive for identity work.
Yes. Yeah. Because I'm
You are saying
Pushing
after
it away,
delta
yeah.
plus, it's always positive.
after delta plus it is always positive.
In order to cancel something, you need that.
You need some contribution within this range, and then you again can optimize this a such that this becomes the smallest it can be, because this is the upper bound, and that turns out to be a equals to this. Okay, and that gives the bound that this is c by 12 plus 3 by 4 pi. Actually, sorry, for delta it is c by 6 plus 3 by 2.
This is just with B3.
This is just with f3 and f1.
Oh.
Yeah. So this is the Hellerman result. This c by 6 plus and this is c by 12.
And the optimal expectation is C by 12, right?
Yeah, optimal expectation is c by 12, and that we'll see can be reached by using the torus with some assumptions about positivity. Is the logic clear?
So you wrote this equation which has one variable a which you can tune, and you tuned a so that the identity contribution
Gives you some definite sign.
some positive sign, let's say. And then there should be another contribution which cancels it, and that constrains this delta.
Yes, exactly.
If you increase P,
Yeah,
uh,
you get higher polynomials.
yeah,
You get higher polynomials.
yeah, so you can do
You get
better
more
than this
roots.
bound. Can you do better than this bound, or you
People
get
have tried,
intervals?
but
You get intervals.
you get intervals basically.
So
So
you can further say that it should in this range it should exist here and here. Is that
no, you cannot say that because it cannot. It may not exist here, but exist there.
so it doesn't really
Not so useful. But this is still an open problem whether we can use all the. So this is part of the optimization problem.
So far you used this was at P equals what?
P equals 3 and 1.
1. So just very simple data.
Yeah, very simple data.
P
So
equals 1 by itself gives you nothing.
P equals 1 gives you something for the torus 1-point function. That gives you, which now. So the torus 1-point function. This is.
also did it in this way.
Hmm?
Hellerman also did it in this way.
Yeah, Hellerman did it in this way. If you break it down, it is this what he did. The paper is longer, but this is the logic. Yeah. So this is the relation. This is the modular covariance statement of the 1-point function, 4 pi square by beta. So from here one can see that the modular invariant quantity is just beta over 2 pi delta O by 2 O beta.
Just let me understand roughly the physics.
Yes.
So if we took just the vacuum block,
Yes.
then this, of course, this thing would not be odd
Yeah. If you just take the.
because it would decay with temperature.
Yeah.
And something has to fix that up.
Yeah. The.
Now,
Mhm.
but what's interesting is that they're saying that things at very high energy can fix that.
No, it's still low.
Yeah, it's this. I suppose you're saying that if something's at very high energy, then it affects what's happening here and here more or less the same way.
Yeah.
Modular invariance.
And this is related
Yeah.
by modular invariance to what it happens.
What is here and here?
Yeah, I mean,
Small.
We're at two different betas going through the
2 pi.
going through 2 pi.
Yeah.
So if something is very high energy, it doesn't really care whether you're 2 pi plus epsilon or 2 pi minus epsilon. It affects it the same way. So it can't really fix up this slope. So it has to be near enough. That's one end. Now what about the other end? Yeah, the other end is simply that it's behaving too much like the vacuum. If it was low enough,
Yeah.
it's not too different from the vacuum. Right. No, wait, this lower bound, is it larger than C or greater than C? Just what are the values?
There's no lower bound. This is just saying that there has to be one bit in this regime.
In this region.
In
right.
this region.
So it was between delta C by 12
Yeah, and
C
this.
by 6.
Yeah.
So the lower bound was exactly at the.
C by 12 is what?
No, C by 12 is not a lower bound on delta. There can be operators also smaller than C by 12.
I
Yeah.
But you said
There has to
one
be.
operator
Has
in
to be
this
one.
range.
Yeah.
Where
Yeah.
are you getting the lower bound?
Oh, from because there is another 0 at C by 12.
So it can only be fixed up by having an operator in this range.
Yes.
Now, yeah, it's sort of okay. I sort of thank you.
Can you tell me the units, please? So what is the energy radiation?
L is 2 pi. So everything is in terms of L.
All the way there.
So energy is delta by L.
Anything lower than C by 12.
Right. But in
Contribute
case you
further
have
to
this
this.
hierarchy of the energy of the vacuum, which would be negative. What is the zero energy for you?
Right.
When you say C by 12,
Yeah.
in what unit? What is set to zero here?
Delta equals to 0 is identity.
Identity.
Delta equals to 0 is identity.
In that unit.
If you use characters, can you do better or not?
No, this is 0.47. You correct after that digit. It's 0.474. You get 0.471. I think.
But what?
Oh, this number is 0.47. 7774 or something, and you go to I think 0.477. You go to 0.471, something like that. If you use character.
No, but analytically 3 over 2 pi becomes
Oh, analytically you cannot write down because you need Dedekind data derivatives at I. You can only You can write it in terms of derivative of data at I.
This kind of thing is not known.
Analytically, in terms of pi, no. But for 1 point function, this is the invariant quantity, because this is same as g 4 pi square by dt. This same. So now one can play the game with this quantity and expand this in torus blocks, but also one assumes that the diagonal OP coefficients are positive.
This is the part which is.
That is a very strong assumption. Yeah. So for example, for Liouville theory in the positive range, from the Dawes formula you can show that you can make this choice, because the Dawes formula doesn't have a pole, it doesn't have any it doesn't cross a singularity or a zero in the physical range. So you can choose all of them to be of the same sign for the diagonal case. But this is a very strong assumption. So
But this is for some Ising model or something, one can see whether it's true. Is it true?
for all minimal models it is true.
It is true.
For all minimal models you have the explicit formula for the 3-point function.
Oh, you can get it from Diozizi.
Yeah, you can get it from Diozizi, and there it turns out to be true. But of course it is a huge assumption. So but this if you break it down, this is beta over 2 pi to the power delta O by 2 sum over all OP coefficients I O I sum over I times the torus blocks I O Q I O bar Q bar, and then what we did is we used the large C torus blocks, which are known in terms of the hypergeometric functions. So these are, just write it down, Q to the power hi minus C minus 1 by 24, C by 24 over 1 minus Q 2f1. Okay, I'm not right. There's some thing here, and then one can again apply the odd polynomials here, and get again one can write in terms of Bell polynomials, and then what one gets in the h bar plane. I'll just draw the regions. So in the h bar plane, this is the line h plus h bar equals to C by 6. This is the Hellerman line. C by 6 plus 3 by 2 pi. And here one can tune O and see what are the regimes of h and h bar, and one can never go below C by 12. One can never go below C by 12. So this is one thing.
Be able to cut off the upper edge.
Hmm?
So you might be able to cut that down.
Yeah. So that's what I'm saying. So basically, so this is the, so again let me tell. This is the Hellerman line. Now from just by considering f1 of O beta. Just by considering f1 of O beta is 0, one can get so one can get a line which is below, such that this functional is negative below this line and positive above, and by reducing O, one can turn this line, one can pull this line down, but never cross C by 12. Okay, C by 12 is here.
Reducing O to what?
And
Reducing dimension of O to what?
yeah, so reducing dimension of O means just choosing random values of O.
Right, but
Yeah.
you are proving a bound on the.
Yeah, so now the optimum so the best thing we can do is choose O to have this value,
Okay, good.
C by 6 plus 3 by 2 pi. Then it turns out that this line becomes C over 10.38.
But if we equate the dimension of O and the line,
Yeah.
then what happens?
Then it goes back slightly. It
All the way, C by 12?
so this becomes numerically we can't see it. So it stops somewhere probably because it breaks. But
So that would be kind of
Yeah,
conservative consistent minimum, right?
that will be the kind of the minimum. So then, but this is using this huge assumption that these C's are positive.
Right, but
so one can do better with 2-point functions because there you get
What is
square.
the higher genus? Partition function with one higher genus and circular.
Yeah, then yeah,
So if you take
I
C
that
dimension
is
of
also
O to be
yes,
very close to 0, then you start getting C by 12.
yes, exactly.
Sorry, I was spacing on.
Yes, yes.
You were using a 1-point function.
Yeah.
And then you got bounds and dimensions of O.
Yes.
Why didn't the magnitude of the
No,
C
I got bounds on the dimensions of all I, all the I.
Yes.
Yeah.
But why didn't the magnitudes of the C's play a role?
Because so I am assuming
So
this
because of the assumption.
because of the assumption basically this is just a positive which I keep outside and look at the polynomials. For 2-point function, this is explicitly I will have a positive square, so I can do better. I can in principle I should be able to say something about I can bound the OP coefficient squared. So there times the means weighted OP coefficient with the spectrum. So there, so I'll just sketch that. That analysis is not complete because I'll tell you. Yeah.
This taking this
Yeah.
result and using in Johansson formula might tell you something. For example, you know this operator exists in
So
between.
another good thing about the 1-point function is that the identity does not contribute. So you don't have to worry about subtracting off anything. That's why just from F1 you get something non-trivial.
But in 2-point function, how about before by bounding the OP coefficient, how about bounding the gap here?
Yeah.
The fact that
Yeah. So that is what I will tell you. Yeah. So we could not complete the exercise, but because in 2-point function you remember the coordinate also changes. So it is not simply just a factor of beta which makes it modular invariant. You have to integrate over the torus to make it modular invariant. So what turns out to be modular invariant for the 2-point function is you have let's say call this f of beta. F of beta is integral over the torus. And g of beta 2 pi by beta 1 minus delta O f of beta. This object is now modular invariant.
Sorry, what about this divergences? UV divergence?
Yeah, so I'll tell you. So then, yeah, good. So I'll just 2 lines to derive this, why this is modular invariant. So if I start with this guy, so I already know that, so this is equal to O W tau O0 for the -1 by tau torus. Times tau power -2 HO tau bar to the power -2 HO bar. And now I am integrating over W torus of the original torus, tau torus. Now this I can write as some tricks. So W prime delta function W prime minus W by tau delta W prime bar minus by tau bar times integral over d to W prime t of -1 by tau. Just introduce this integral. Now I change the delta function from delta function on W prime to delta function on W. So I have there is a 1 factor which comes out, and this becomes W minus W prime tau, becomes W bar minus W prime bar tau. Now I integrate over the original torus. This is just this just gives you 1. So this tells you, so this is basically tau to the power 1 minus 2 HO, tau bar to the power 1 minus 2 HO bar times f of 4 pi square by beta.
You're performing the modular transformation on each correlation function that picks up some factor,
Yeah.
and then you have to change the measure.
Yeah, you have to change the measure, basically. Yeah, that is what is happening. And but you are right that this integral will in general have some divergences, UV and IR. UV divergence when the points collide. So that those divergences will be there, but at least in the naive analysis, when you take all the operators, you still can do this analysis. You can still do the integrals.
But if the dimension of O is large,
Yeah.
is small enough, then there's no divergence.
Yeah. Yeah, so 1 by square root. I think, yeah, if you integrate 1 over square root of tau d tau, then there is no divergence.
Yeah, I was just thinking if the dimension, if it's a marginal operator,
Yeah.
there would be a divergence.
But you want to
You can
bound
have
the
a
gap.
non-trivial.
No, O is in your hand. O you choose. O you can choose.
No, I cannot. I cannot go below the bound, right? I want to bound the gap.
You want to,
The lightest,
yeah.
lightest operator above identity.
That is true,
whatever
that is
bound,
true,
I
that
don't
is
want to
true.
take it below that.
Yeah, that is true.
But you might
But,
modify this kernel. You might have some modular.
No, but Vijit, one thing is that even with arbitrary O, you still don't know what are the shapes of the regions that you get, where you have 0 and non-zero. So say, so for example, what we get is by choosing some, so that's why this is incomplete. So we get an island where this has some particular sign, but we also get some non-compact region where it also has that sign by choosing some combinations. But say ideally one would like to have some small island somewhere. By and this island doesn't depend on this, means basically so this island is obtained say by considering f5 plus a1 f3 plus a2 f1 equals to 0. By choosing these guys will depend on O, and this just gives you constant on H. Here we did delta and delta prime. But this analysis is incomplete. Yeah, so.
But you can modify the kernel which is your integrating. You can have some modular form of degree 1 or something to change this domain. The function f of beta that you have, you can change that.
Yeah,
Get some
yeah. One has to come up with, that is the challenge in this game.
with suitable modular forms while integrating.
What is this defined through a dimensional continuation? Continuation and dimension of the operator.
What?
I mean, you've got a let's say you've got some integral.
Yeah,
You want to make sense of it.
yeah,
If you define that integral through dimensional regularization,
yeah.
where the dimension is not the space-time dimension,
Or the operator.
Operator
dimension.
dimension.
Yeah,
then can you still argue that this dimensionally continued integral
Yeah.
is modular independent?
yeah. That is, yeah, that.
If you can,
Then one
then
can,
you might be able to get it.
one can analytically continue to
Yeah.
that bound. Somehow, yeah. So this is incomplete analysis, but maybe in little bit I'll tell you also little bit about the.
Yeah.
Or-
No, we need lunch as well.
Yes. Yeah. So this is the last thing. I'll just sketch why there is a problem with the Cardy analysis now. Okay, but this is.
Sorry, what was the punchline of this intermediate regime?
Yeah, punchline of this intermediate regime is that with torus correlators, one I just sketched away to
there's
get.
an idea of how
There's
to
an
do it.
idea of how to
And the 1 point business gives you something, but with some assumptions.
with some assumptions. Yeah.
And but I keep seeing papers on the internet saying that they've
Yeah.
bettered Hellerman's bound.
But not by much actually.
But what is their method?
Their method is choosing this functional, choosing higher derivatives
But
and
not
sophisticated. No. Yeah. In that sense, this is a different way.
But is it just incremental, like very close to Hellerman?
It is, but I think Mazak and Hartman is slightly better. I think.
How much?
I think.
CO plus CO12, right? They have CO12 plus stuff. No?
Do they? That I am not sure. I think they still. I think it is better than the 1 point function which I showed. So Hellerman is C by 6. What I showed with 1 point function is 10.38. I think Mazak is 9.1. It's better. But this I don't complete. I have not gone through this in detail.
That is an expert on this extremal function.
On the extremal
The
function.
game is you want to tune your functional
Yeah.
so that it's extremal.
But
Actually,
this
as
it
much as
but they still work
not
with the
only can you prove a bound,
yeah.
you can also show that there is a
Function.
theory at that.
They at
So in
that.
that sense, you have done the best that you could. That's called extremal functions.
But still they are working with partition function. They are still working with the partition function. So maybe there will be some extremal version also of these one can do this for the
I'm
correlator.
not understanding why you're saying C by 9.1 is better than C by 10.3.
Upper bound.
Yes.
Oh, sorry, say by 10.38 is better.
Yes.
Sorry.
That rests on this.
Sorry. This is also part of the typo in my abstract which I sent, because I sent it improves from C by 12 to C by 10.38. Okay, sorry. Okay, I'll just go back to the Tauberian analysis. Yeah, here I'm putting in more information. I'm getting something more out of this.
I think non-contributing identity was probably mean.
Yeah, that and this assumption that everything is positive. Okay, so very quickly about this Tauberian techniques. So say if I consider this summation, and suppose that x equals x going to 0, this has a divergence like 1 over x. Then clearly when all the an's are 1, this is true. So I want to figure out something on an, some constraints on an such that it reproduces this divergence at small x. So that is what we have been doing in this extreme Cardy regime. So these Tauberian results, what they give us, what the result it gives us is basically it tells us something about the average of this quantity.
Better than doing inverse Laplace transform.
It's better than doing inverse Laplace transform finally. So this tells us that this is approximately 1 for n going to infinity. So it's kind of average of these these coefficients that these techniques will give you finally. Okay, now what this is doing and where Cardy is going wrong means it all stems from the fact that rho delta is a sum of discrete delta functions, and we are trying to approximate it by a continuous function. So that is the main issue here. So what we had for rho delta was this expression, epsilon minus I infinity plus I infinity d beta or beta delta e power 4 pi square by beta c by 12, and then there will be of course.
Sorry, just
Yeah.
What is the statement? Is the statement that Cardy's result is wrong? What is?
No, so the statement is the assumptions which go into Cardy's result, that firstly that high temperatures give you means is dominated by large delta. That is one assumption which goes in,
Okay.
and then and finally relies on the fact that you are doing this inverse Laplace transform,
Yes.
and you are approximating it by a saddle.
So Cardy's analysis of the partition function is beyond question. The partition function at small beta is clearly given by the other guy, right? But that is not.
No, that has also been questioned by.
That's also been
Yeah, that is also. So I'm just talking about that now. So this, because these has these corrections, right? This is minus 4 pi square by beta delta chi minus c by 12 is there dot, and these are suppressed when beta is real. But I'm integrating over the entire imaginary axis. So when beta goes large and complex, then these are order 1, and degeneracies keep growing. So this is divergent, and it is good that this is divergent because rho is a sum of delta functions.
Okay.
So
No, but just for real beta.
For real beta,
statement
it is-
about the partition function is not big question.
no.
It's just the consequences of that statement.
Yeah.
For the density of states.
Yes, exactly. Yeah. For the Cardy formula.
Yeah.
Yeah.
Okay.
So what one wants to do is cut off this integral somehow.
But you're not, in the end, Cardy's formula is thermodynamics, and you're not going to claim that thermodynamics is not right.
No.
So you will find some sophisticated corrections to the formula.
Corrections means basically a way to control the errors in the Cardy formula.
Fine.
Yeah.
Fine. But
That's
the
it.
formula is correct.
Formula is correct. Yeah. So basically, we'll show that the corrections go like, and the corrections also go what you get from the corrections to the saddle of the Cardy. But that is kind of formalized in this approach. But it gives you some other interesting things, which I'll some more coarse-grained things about how fat your band can be to have at least one primary operator. Those things come out of this analysis. So here the starting point is to start with this kind of a band. So and then find approximations to this. So by some function which one can somehow find out, means some kind of sinc functions which some upper and lower bound. So this function, let me call it phi plus, this I call it phi minus. So this theta function, which is this function which is one only within this band.
So rho is defined with this smearing.
Yeah, rho will be defined with this smearing. So what we will try to find is something in this sense of averaging. We will try to find a number of states within this.
Smeared by this.
Smeared by these functions.
Yes.
And this was this window in Hellerman. What is this window?
No, this is
Delta minus.
yeah, this is right now arbitrary, this delta.
Right now arbitrary, but you might focus into something.
Yeah, so we'll take it to be order 1, but we'll show that it cannot be too small. Also, it cannot be too large. So this is bounded by this phi plus above and phi minus. Now one can trivially multiply this in this range. This is trivial to see that this is if I multiply by delta plus delta minus delta prime. This is exponent which is positive, means which is greater than 1 within this range. It's like this, some function like this. This is 1. And here similarly I multiply by e power beta. Beta is just a parameter now. That is the interesting thing, that I don't have to focus on. I can tune beta to be. This is delta minus delta prime. Now I multiply. Yeah. So 5 minutes. I'll just sketch what is going on and what is the important thing. So if I now integrate with the actual density of states, d delta prime, this counts the number of states here, and this I multiplied so that I can get a partition function out. That's why I multiplied by these factors, and rho delta prime d delta prime. Now to get the partition function out, I can write this in Fourier space. This phi minus from delta prime to this Fourier space.
Sorry, the smearing function is not there on the left and the right.
Yeah, there is.
Phi is this theta.
Phi.
What is theta?
Theta is just a step function.
Theta is a step function.
Theta is a step function such that this gives you integral. This becomes an integral d delta prime from delta minus delta to delta plus delta.
That's just number of states.
That's just number of states within this range.
And then you've shown that it's less than equal to what?
Yeah, this and this.
Oh, and beta is anything. Because
Beta
it
is a
works even
parameter.
at beta
Yeah,
equals
exactly.
0.
That is the advantage of doing this analysis. Beta is in your control.
And how do you know that? Oh, it's just that this clearly has more states, and how do you know one of them clearly has more states?
Yeah, this
Over
one has more states.
Clearly has more states.
Yeah.
So how do you know the other one has less states?
Yeah,
Because
so
it goes negative,
yeah, it goes negative.
I see.
Yeah.
Yes.
And then if I now still I cannot write this as a partition function because of this phi minus.
Yeah.
So I write this as dt phi hat t e power minus it. I write it in the Fourier space, such that this thing now becomes dt phi minus t, and then this I pull out this factor e power beta delta minus delta, and this other thing I can combine to write it as z of beta plus it times some exponential factors which are with the c. So minus beta c by 12 minus it c by 12. But now you see that this is almost this is exactly same now, because you are still integrating over imaginary temperature from minus infinity to infinity. But now if you are clever with, but now this function is in your hand, this phi minus. There was nothing like that here. So if you choose this function to have support, finite support, then I can cut off this integral. So that is what this Tauberian analysis is doing. So choosing these functions such that same function, for example, has kind of finite support, so it cuts it off and regulates these errors.
You're very crucially using that the density of states. I mean, the integrand is positive, right?
Yeah, this is a unitary theory. Yeah, this is a unitary theory. Otherwise, this inequalities will not work. Yes. And of course, now you see that.
How do I know that if I cut this
Yeah.
transform off, I should get something that I wanted, meaning it should lie below this step function?
No, you have to choose that, and you have to choose. Yeah.
But the fact that it was local on delta space.
Yeah. It is not so local. That is a very good point.
That you are
Yeah.
making
So
it not so local.
no. So if you squeeze this further, then in the Fourier space it will keep extending. Then it means there is a delta minimum which comes out of this analysis.
Right.
So
There is some optimization.
yeah, there is optimization in choosing these functions, and these are right now just guessworks. Srideep Pal has used some information theory techniques to come up with a nice function, which gives you this delta minimum is actually 2 times delta minimum. This width is 1. So basically, if you or in another way to state this result is if I look at least width 1, I will have at least one primary operator in that window for any CFT.
Oh, okay.
Yeah. So then
For large enough delta. For large enough capital delta.
no, this is
Any delta.
no. So for large enough capital delta, because we will use actually we will optimize also this beta. So I'll not state the steps, but just a little bit. Next, what one does is one splits this guy into the vacuum contribution.
Have you
Yeah.
removed the descendants? in this
No,
analysis?
one can do it with also the characters. One can do it with the
So
primaries.
there's a primary in it.
Yeah, this is primary. This
Otherwise it would be.
no, yeah. Yeah, exactly. This is just for primary. Sorry. Yeah, this is just for primary, and so this is what it buys you, and then you also crucially you separate this out into Z vacuum plus Z heavy, and you use this results by Hartmann, Keller, and Stoica, and using those results you can show that this is suppressed, provided you also choose this lambda to be smaller than 2 pi. So there is also a condition on the Fourier support. It cannot be too large. Then the heavy states also dominate. So these things you can again repeat for all the for the pillow and for the torus correlators and other things, and you will get, for example, for the torus correlator, for this channel exchange you get 2 delta minimum is square root 2. And another thing that you can prove using this analysis is that if I look at the 2-point function, heavy, light, heavy, and say the lights are separated in time, then this approximates light in a thermal state. But this approximation with the ETH temperature of beta, but from this analysis you can actually prove that this is true only when T is less than equal to beta. For only times, time, and this was noted by this monodromy analysis of 4-point function by Faulkner and Wang. But here you can actually prove this, that T.
What to make of this? That you can.
So if operators are,
You can distinguish between microstates.
between the microcanonical and the canonical ensemble.
But this is a very small time.
Yeah, this is a very small time, because this goes like 1 over square root delta, 1 over square root heavy.
Or in the large C theory, beta could be order 1, right?
Beta could be order 1.
Beta could be order 1 for a very heavy operator.
no, so
And
the,
sometimes-
this cannot distinguish. So if t is less than it cannot distinguish.
No, but say that number on the right hand side was 10.
Okay.
So you're saying at time equals 12, you can
Yeah,
distinguish.
yeah.
Are you sure? I mean, are you saying that you can? Are you saying that? Is it a one-way statement or a two-way statement?
No, it is a one-way statement.
Yeah.
It is a one-way. It is no, it is a one-way statement.
Yeah.
It is a one-way statement. Yeah.
I mean, this is, if you could always distinguish at larger, when you go outside this, that would be very surprising. Because it would be like a black hole, a very heavy state can be distinguished from a black hole at times of order 1.
So no, but the one-wayness is if I have this, I can
When you have this, you cannot distinguish.
I cannot
But you're not
distinguish.
saying that when you don't have
Yeah,
it, you can distinguish.
yeah.
So this bound can be improved.
We are not sure about
I mean, at least in large C context, certainly. It would be very surprising.
that. Should be surprised.
Want it to be order C.
Something. C or into C.
Yeah, that's kind of it.